All right. So today the goal is gonna be to finish that lecture that we were going through last class, and then most likely complete our randomized complete block design mixed effect model, which incorporates an extra random or incorporates one random effect, which we have not done yet. So if you are on the course webpage, you can go ahead and launch that presentation if you wish, or you can just follow along with me where we're talking about fixed and random effects. So I'm going to do a quick recap and then pick up where we left off last time. So when we're running statistical models, we normally have this option of treating a given explanatory variable as either fixed or random. That's going to depend on a few things that we talked about, and we're going to just cover that very quickly here. But basically, up until now, all the models we ran were fixed effects because we were interested in very specific levels, so very specific nitrogen rates, potassium rates, or anything that's very specific to your study. Most of the time, your treatment design, regardless of your area, most of the time that's going to be a fixed effect. There's some cases where it's not, perhaps if you're working with breeding trials or some other types of trials that you're really interested in the variability and not just the mean. But for the most part, we're interested in the mean, and therefore we treat our explanatory variables as fixed effects. So every single model, even a fixed effect model, has at least one one source of variation or error. And something very key to keep in mind, and just a refresher, is that basically so the error is what's associated with the residuals. The residuals is what we check for model assumptions, basically meaning that every time you have a source of variation or error, we need to check for the assumptions of that. If we just have a fixed effect model, then you can use LM in R. A model looks like this, where basically you have your observation, overall mean, the effect of your treatment as alpha I, and then EIJ is the residual of that model, which is basically the source of error of that model. And then every time you see something like, something is explained IIDN independently identically distributed normal with a mean of 0 and a given sigma square. This basically means that that's a source of error, and that these are basically this sentence here is what summarizes the assumptions that we're checking on the residuals of every single model. So fixed effect models do have a source of error, but just one. Random effects model, on the other hand, are models that we're fully interested in the variability or the variation of a given factor. And we don't really care about the mean. So the mean of nitrogen 0, the mean of nitrogen 50, I don't really care about that. It's more about how the variability of the levels I chose represent a larger population of nitrogen levels. And a random effect model really only has a random effect model has more than one source of variation or error. In R, we're going to have to use a different function. There's one function LMER from the package LME4 we're going to be using. And this, because this function allows for the computation of an extra source of variation or error. So there's an example of a fully random effect model where we have still our observation, our overall mean, the random effect of a given nitrogen rate, in this case, and then the error corresponding to that model. So in this case here, we have two sources of error. So we have the distribution of that alpha I is going to have its own distribution of sigma square, and then still the distribution of the residual of the error, which we normally have for every model, as I was telling you. So in this case here, a random effect model, a model that is fully random, basically means that the only fixed effect is the overall mean, but we don't have any treatment fixed effects. The treatment effect here is treated as random, and then we have the error of the model. So we have two sources of variation in this case, and each one of them are modeled separately and independently. This plays a role on the variance of a given observation. So for in this case here, a random effect model, the variance of a given observation is sigma is coming from the addition of the sigma square of that random effect plus sigma square of the residual or the error itself. And if we compare this, well, we talked about some different ways of estimating these. We're not going to get into a lot of detail here, but basically we need to know that what we want to use is the restricted maximum likelihood, as that's going to be our model that is that produces unbiased estimates of that error of the variance that we're estimating. Okay, and then we had the conversation about should I treat is a fixed or a random effect? So again, if you're interested in the mean effect, then you should treat as fixed. But sometimes, even if you don't care about the mean effect, for example, I really don't care about the effect of the mean effect of block. I have no interest in doing a pairwise comparison of block 1, 2, 3, 4 with the means on yield and understanding how that is playing a role. So I really don't care about the means of blocks. Can I just treat that as random? So we went through this conversation here. So if you do want to know the mean of given factors, then it should be fixed. If you don't care about the means of each one of those levels of that factor, then we need to answer a few questions to be able to say, okay, let's treat this as random effect and appropriately treating as a random effect. So if you are interested in just using those levels to understand the variability of the population, and if your levels were randomly selected from a population of potential levels, and you have enough of those levels, then you can treat as random. So just a quick example here again. So let's say my blocks, right? So I don't really care about the mean block response on yield. I don't care to know the block 1 had yield X and block 2 had yield Y and how they compare. I really don't care about that. The block is just there to help me to capture that variability. So I'm not interested. So the first question here would be, no, I'm not interested in the mean of the blocks. Now, are you just using those levels from a larger population of blocks? Yes, I guess we could say that. However, were your levels randomly selected from a larger population? Most likely not, right? As we talked about, at least on the field, you have your blocks right next to each other. So they probably don't represent a population of blocks in that farm, for example. And then do you have sufficient number of levels? So do you have at least 5 blocks? In my studies, this would be a no most of the time because we do 3 to 4 reps in general. So 3 to 4 blocks. Perhaps in your areas, you would have more. And then so you could treat it as random if you wish. And really the key part here of the sufficient number of levels is because to reliably estimate a variance component, we need more degrees of freedom for that as compared to mean. So mean, we can estimate reliably with less number of degrees of freedom compared to variance components. So if you have less than, let's say, 5 to 8 blocks in the example we're talking about, your variance estimates would not be accurate, which could impact everything in your model. So again, a classic example is blocks in an RCBD. Should you treat it as fixed or random? People do both ways. They're going to see both ways in the literature. When you're reviewing papers, when your papers are being reviewed, you're going to see that perhaps somebody's going to come up with this question to you. Why did you treat it as fixed? Why did you treat it as random? And then, it's useful to know how to defend your choice. All right, so then I think this is where we stopped. So we talked about fixed effect models only have fixed effects, and the only source of variation or error is the error of the model. Every model has at least one source of variation, even fully fixed effect models. A random effect model, on the other hand of that, is going to be a model that all of your treatment factors are random. So for each treatment factor, you're treating that as a random effect, which means that it's going to get its own source of variation, plus the source of variation of the residual that every model has. Now, there is something in between. There are mixed effect models, which is probably most likely what you're going to use in your research. So a mixed effect model basically contains both fixed and random effects in the same model. Because it has at least one random effect, it also has more than one source of variation or error. We're also going to be able to analyze this using the function LMER from LME4 package. There's going to be a few other packages and functions that can be used as well, but to start off, we're going to talk about that one. And if we look into a model, so let me just walk you. So this is, I guess, new content for today. So if you want to make sure that you follow here and ask questions if you have. So we still have Yij as our observation. In this case, we can think of yield observation. We still have an overall mean. And then in this case here, I'm treating rho j as the random effect of block. So now I'm treating block as a random effect as compared to treating as fixed effect before. Alpha I is still the effect of nitrogen rate. And then we have Eij is the residual that we have after all the terms have been taken into account. So now on this mixed effect models, because I have one random effect, I have the distribution of that random effect. So alpha I, here's the effect of the block, is independently, identically distributed normal with mean 0 and sigma square A. And we also have that error term that every single model has that's based on the residual. Something to notice is that even though they look, the specification here looks very similar, but the sigma square is a different term, right? So for the random effect, the sigma square A is representing just the variation among blocks. And for the error, sigma square E is the variation of the residual of the model. So there are two different sigma squares being taken into account into this model, which then, similarly to random effect models, the variance of an observation is going to be expressed by the combination of both of those variances. So the variance coming from the block, the variance coming from the error or residual. Something that's really interesting, and I think you're going to notice that today in the exercise, is that sometimes by treating, so you have this option, you have this choice of treating your block as fixed or as random. You can even play around with it if you want and see what makes sense. The key thing is to have your block in the model if you properly designed it, but then treating as fixed or random, is a choice you have, and it's going to have some repercussions into your results. What happens most of the time is so let's say our RCBD with blocks fixed, the variance of a given observation was just related to the variance of the residual. There was no variance related to the block because the block effect was being, I guess, sucked into the mean effect of the block and not into the variance of the block. Now that we treat block as random in this case and have a mixed effect model, the variance of a given observation incorporates both the variance of the block and of the residual error. Meaning that after all, maybe the variance of your observation is going to be larger if you have blocks as random compared to fixed. And then you can think, well, how can that be a good thing? How can I increase the variance of a given observation be a good thing? I thought we were trying to reduce the variance so we can more easily find treatment differences. Well, that is true. However, another point that you're going to see on this exercise, on the split plot exercise, and then on the repeated measure exercise is that having the lowest variance, we should try to get the lowest variance while taking into account the proper structure of error of that study. So what I'm saying here is perhaps if you treat blocks as fixed, yes, your variance of a given observation may be lower. But is that truly what happened on the field? Should it be lower? Or maybe in the field, actually, it was higher, and now you're just underestimating it and fooling yourself. So there is this trade-off here between, okay, sometimes we do things with the model that actually increase the variance. And not that that is a good thing, but that is just what should be done. That's actually what happened on the field, is the structure of the error that your study has. So you shouldn't just ignore it to get a lower variance of an observation if that does not represent what happened on the field. I know this is like a lot of words, but at the end of today's exercise, I think you're going to be able to see some of that effect. All right, so again, with a mixed effect model, the variance of your observation is going to be the sum of the variance of the block and the residual error related to that observation. So in our motivational example here, talking about a treatment design, so still our 2A factorial, 3 nitrogen rates, 3 potassium rates, so 9 total treatment combinations. This is just a refresher on what we've been working with. And in our previous RCBD exercise, we analyzed that with blocks as fixed effects. And really, you didn't have to do anything for it to be treated as fixed effect. You just put that in the model. And that's the default behavior. If you just put in the model without explicitly saying it's random, then it's going to be treated as fixed by the modeling function. So now our goal is going to be to treat blocks as random. And then because of that, so blocks will be treated as random, but potassium and nitrogen and their interaction are still fixed because we do care about their means, right? I want to know what's the mean yield coming from each one of those nitrogen potassium rate treatments. So nitrogen and potassium are still going to remain fixed effects, but now we're going to treat our block as random and see what happens with the model. So I do have here, you're not going to have a quiz today, but maybe one next class about this reading. So I uploaded this paper as one of your reading materials, I believe, for today's class on the class website. So it's a paper by Dixon saying, should blocks be fixed or random? Please go ahead and read that, at your leisure. And then we may have a quiz on this at some point. All right. Any questions about this lecture? All right. So if no, I think that, as we're going to be coding along in class, this next exercise, which is going to be just treating our blocks as random and therefore have a mixed effect model, I think that's going to help to solidify some of these concepts. So I sent an email earlier today asking for you to go on your 2025 DSA local copy of the GitHub repo, do a git pull, and get the latest script that I uploaded this morning for today's exercise. That's on the 04 class code folder of the 2025 DSA GitHub repo. Once you do that pull, you just copy that script. It's going to be the latest script in that folder into the same code folder of your 04 RCBD exercise. So I'm not asking you to create a full new project, a full new setup from scratch. We're just going to be copying this code from 2025 DSA to the current 04 RCBD code folder on your computer. So please go ahead and do that. I'm just going to browse here to my files to get to the folder as well. And then once you move that script into that code folder, just go ahead and launch that RStudio project. All right. Was someone not able to get to this point? Does somebody need more time to catch up? If you need that, let me know now. Otherwise, I'm going to start.
Yeah. I think I wasn't able to do the pull. I tried and then it says it's already updated, but I've not seen the new code.
Anyone else having the same problem? Okay. So Swabir, if you remember, so the way that we're doing that, let me just open here and show you. So you would have come to your 2025 DSA on your computer and then open that RStudio project at that level. I don't have one here, but you would on your side. And then once you do that, it's going to open that 2025 DSA RStudio project. You're going to see that on the top right. And then you just do a git pull by clicking on the down arrow. That down arrow is going to bring the latest script that should be on the 04 class code. RCBD mix partial. Yeah. Yeah. So the latest one is the RCBD mix partial. Yeah, RCBD partial was the one that we did fix effects. We're able to get it, Sobir?
When I did the git push, it says already up to date.
But so when you look into your folder, so on the 2025.
Sorry, Professor. He
Mhm.
said he did git push. He didn't say
Git pull.
he did.
So if you
Sorry to
did,
interrupt. I thought maybe he made a mistake.
yeah, no, that's, so you're doing a git pull, Swabir?
Yes.
Okay, so maybe, Aminder, can you connect on, are you on Zoom?
I can.
Okay, so Swabir, Aminder's gonna connect on Zoom and maybe try to help you through the chat. Because I think you'll be able to catch up once you do that. Yeah, so Aminder, you can maybe ask him to check if he has the script already on his 04 class code. And if it's there, then it's there. He just copies and if not, then yeah, maybe do a git pull again. But yeah, so Swabber, we're gonna get started, but Aminder is gonna try to help you on the chat. Yeah, I think I think if we get to the model chunk, subsection E, if we get to that point and you don't have figured out yet, let me know, because that's gonna be the main point for you to be able to code. All right. So our goal here with this script is going to be to basically run the full analytical workflow of an RCBD as we've done before, except that now we're going to treat blocks as random and therefore have a mixed effect model because we have one random component and then we have still our nitrogen, potassium, and interaction of those as fixed effects. So both fixed effect and random effects in the same model makes it a mixed effect model. So that's what we're going to run today. I think you should have all of these packages already. So just go ahead and hit the play button just to load them. If you don't have, perhaps, I don't remember if you already installed LME4. If you don't have LME4, then please go ahead and install it. You know how to do it. Remember to not leave a install.packages function active in your code. So if you want to install that, go ahead, but then either comment that off or delete that from your code. And again, I will always be telling you this, that while we're using the same data set to run different analysis, experimental design analysis, we're doing this for teaching purposes so we can see the same data set progressing through different analysis. However, this is not how you do on your side. You would always have your own design already determined and you just use that design to analyze your data, right? All right, so let's read in our data frame here. Okay, so to get pulled. So Swabber, maybe for now, what you can do just to make it easier is just download manually from GitHub and then copy and paste like we've done in the first exercise. And then after class, make sure you reach out to Amrinder and he can help you out and see what's going on your side.
Okay.
All right, so first thing here within the data, I left you the code already because this is, if you've done the CRD assignment, this is the third time we're doing a lot of these steps. So all those steps that we have already done, I'm not gonna ask you to just redo them. We're just rerunning and just getting the results right here. So again, data set has 36 observations, 5 columns. We have nitrogen, potassium rates, and then yield, and also our wrap or block information. If you remember, we have to do some wrangling on this data set. This is just that raw data again. So we need to do some wrangling here that is going to be very important for our modeling, which is what? What were we doing that was really important here based on how R is interpreting our columns?
You switch things to factor.
Yes, so she said switch things to factor. So which things?
You need to switch the N rate, K rate variables and the rep.
Perfect. So yeah, we change rep, N rate, and potassium rate to factor because we're interested in an analysis. Well, we change N rate and potassium rate to factor because we're interested in an analysis of variance, which means you want the mean effect. If you were looking for a regression, which does not work with mean effects, a regression would be if you do, if you imagine nitrogen rate on the x-axis and yield on the y-axis, imagine just a scatter plot and then you're fitting a line through it. We could have done that by keeping N rate and potassium rate as double, but that is not our goal in this exercise. Our goal is to do analysis of variance. We want to know the mean effects. Yes, so on the next chunk, while we're checking a summary, we've checked the summary before, is basically just us, doing some EDA. Always do EDA in your projects, always check, make sure that your values at least make sense when looking at these summaries. Also, normally do a glimpse, which is another way of looking to it. Just give us some values. It tells us how R is interpreting those columns as well. And every time you're running ANOVA, make sure that your treatment factors are actually interpreted as categorical or as factor in R. So that's what we're doing this next chunk here on the wrangling. I already left you all the code because we have already done this a few times, but we're just changing rep and rate and potassium rate to factor, and then also creating that extra treatment name column that is just pasting nitrogen rate, adding a plus in between, and potassium rate. So if you go ahead and run it, you should see it on your side. Those changes taking place. So rep, nitrogen rate, and potassium rate as factors. I just did another summary again, just because now that we changed some variables, it changes a little bit how they're interpreted. Just wanted you to understand that as well. But really, at this point, the key summary variable we're looking at is still yield, and that has not changed. So we have 4 reps, 4 blocks. The number of treatments, we have 9. We have 36 total number of observations, and we have yield that varies from about 2,700 to about 7,400 kilograms per hectare. As always, and so, we're not going to be talking about the same thing over and over, but at the same time, I want to leave all the pieces of this workflow in place so you remember that these are important and you should do them, right? So we have already looked into these plots before. We've already seen the box plots of nitrogen rate and yield. We already talked about that does not seem like there's a strong effect of nitrogen rate. We moved then next to the potassium rate box plots. Same thing, at least visually, does not seem like there's a lot going on. And then finally, we looked into one of the potential ways of looking at the interaction between nitrogen and potassium. And here it seems like something is going on, right? So we talked about just from an EDA perspective, maybe the main effects are not significant, but looks like interaction could be. I know that, we discussed about how to even interpret a plot like this. Always keep that in mind because that's not like a skill. Of course, in this class, we're going to flex that muscle of interpreting the data that you see in front of you. But this is something that is a skill you're going to develop for across different courses and especially for your own research. So always, think of ways on how to interpret what you're seeing when you plot data. We talked about the set to zero versus sum to zero restriction. R does by default the set to zero. We want to change that to sum to zero. This can have an impact, or this will have an impact on your ANOVA table's p-value significance. So if you do not change it, you will have a different you may have a different outcome on the significance of your ANOVA, which then messes up your interpretation of it and how you extract means. So always a good approach to change that option. So make sure you run it. Oh, I just noticed I have the wrong script. I have the RCBD partial, so I'm sorry for that. Yeah, thanks, Aita. Now I'm just in your comments. Yeah, so I think I actually did not fully copy the partial script. Let me go back and copy that. It's not gonna, so I really only notice now because this is the part where things change. And then I notice, okay, this is now the code that should be here. So let me, on my side, make sure I get that script, but you already have it. Problem fixed. Is this? Yeah, so maybe there's a little bit of a difference in the comments here, and there will be more comments on the modeling side, but I think for the most part, everything should carry over. Yeah, okay, perfect. So yeah, so Sweber, so this is the part that we're going to be coding differently. So if I guess it would be good if you were able to get to this point and got the code on your side. But if not, then I guess you can still watch along. But then at the end, definitely follow up with Amrinder. Okay, so again, the function LM in R only incorporates one source of variation, which is the one associated with the model residual, which every model has. So if you're running a fixed effect model, as we've been running until now, LM is your function. That's what you need. However, if you want to run either a fully random effect or a mixed effect model that incorporates fixed and random effects in the same model, you're going to need a different function. LM is not going to work for that. LM does not even have the arguments that would take care of that. So there's maybe more than just a few packages and functions that could do mixed effect models. I want to teach you the most classic one, which is coming from a package called LME4. And the function that we're going to be using is going to be called LMER. This function here is going to allow us to incorporate different random effects into either a random or a mixed effect model. And those random effects, in our case, we're just going to have one random effect, which is the effect of block. But as you're going to see on our split plot, when we get to the split plot exercise, we're going to have more than one random effect. And then the way that those random effects are related to each other becomes really important. So LME4 package and function LMER can help us to not only add random effects, but also to specify what type of relationship they have. So is one random effect part of a hierarchy where you have I guess I'm not going to tell much to not get you confused. So let's just think of our case today of one random effect. So make sure you round that options for the contrasts. And so here, if you come on the model fitting part of this chunk, this is where we start coding with me. We're just going to use the Simon symbol. Again, the function name is LMER from the LME4 package. The model specification starts very similarly. So let me just take our data set name, which is RCBD DFW. I just want to print that below so we have the variable names. We can look into them. So we're still going to say that yield kilograms per hectare is our response variable. right? So response variable is what comes before the tilde. So we're explaining yield with our explanatory variables. So let's do first our fixed effect part of this model, which you're already familiar with. So for the fixed effect, it's just like before. We're going to use N rate, asterisk, potassium rate. This is our fixed effect part of the model, right? This is exactly as you've done with LM before, so nothing new here. Now, let me ask somebody if somebody can remind me. So on the previous exercise with RCBD as fixed, there was one more thing in this part on the right side of the tilde. What was that? Okay, data was there as well, but I guess I'm trying
Plus
to
rep.
more on the formula side,
So that would be rep, the
Rep.
block effect.
right? So we had a plus ref. This is not even going to work on LMER because LMER is expecting a random effect, but I just want you to remember that before on our full fixed effect model, this is how we specify things, right? So all of them were fixed effects. Now with LMER, when we want to specify our random effect, I'm just going to break line here to make it a little bit easier, but I'm still right after that plus there here on the right side of the tilde. So we want to tell it that we want it to treat block as a random effect. The way that we do that within LMER syntax is to open and close parentheses, put a 1, a vertical bar, and then the name of the variable you want to be treated as random. In our data set, the variable is called rep. So that's why I gave a 1 vertical bar rep. So this is basically the way that you tell the model what variables you want to be treated as random. And notice that for variables that are being treated as fixed, there's nothing special about them. We don't have to tell it, hey, these are fixed. It's going to treat them as fixed if you just give their name. For the random effect component, then there's a special way for it to specify, which is using this syntax here. So you're always going to use this, and then you just change the name of the variable that comes after the vertical bar. This is basically telling the model that we want reps to be treated as random.
More than one, which is like, do like one and then another quotations 2, and then another quotation 3 with all the vertical line, or is it all gonna be like one vertical line?
So Zach's question here was about if I have more than one random effect, how would I specify that? That's gonna come down to how those random effects are related to each other, if they are related to each other. So for example, you could come here and just add another random effect if you had another variable that was treated as random. So maybe you have like location, perhaps. You know, it could do something like that. But then basically you're not telling the model that rep and location are connected. So one example that we're not gonna get fully into this, but I just want to give a quick spoiler. If you have multi-site year designs, so let's say that this design here, let's say that I had 2 sites, 2 locations in this one data set, and I wanted to analyze them together. The way that a multi-site, in this case, multi-site analysis would work is you would nest block inside location. That's how you would do a multi-site analysis in one model, right? So let me take one step back here. So let's say you do the same trial in 2 locations, and you want to analyze the data from those trials completely separate, even though they have the same design, everything is the same, but you want to analyze them separately with 2 different models. You can do that. Then it's not a multi-location trial, or it's not a multi-location analysis, I guess, because you just have one location, one analysis, another location, another analysis, completely separate. However, if you are interested in the location effect, you want to be able to tell this location was significantly different from that location in yield, then they have to be together in the same model, right? You have to have both locations in the same model, in which case it becomes a multi-location model. If that's the case, and if you had randomized complete block design as your design, then the way that you would treat your random effect is by nest rep inside location, which in LMER syntax, it would basically be like this. So you have the larger hierarchy factor coming first, and then a forward slash, and the smaller factor after that. So this basically means rep is nested inside of location. We're not going to be doing that here. We don't have a location effect here, but that's how you would do. Yes, Comfort.
Yeah, I wanted to ask that, do we always have to nest rep in location? Would it make sense to say maybe +1/rep, then +1/location?
Okay, so Comfort's question is this the same as doing 1 rep plus 1 location? So the answer for that, Comfort, is that is not the same. So when you're doing this, you're basically telling that you have 2 independent random effects. And when we do the nesting, they are not independent anymore because they have a hierarchy that they're following. So really, when we specify this behind the scenes, this breaks down into location by itself plus the interaction between location and rep. So this syntax here breaks down into this. And as you can see, this is not the same as this, right? So here we're basically saying that rep does not get its own main effect on the variance component. It is associated with location. So because it is under location, there is a hierarchy in that sequence. Yeah.
So do we say the first one is like the right way to do it instead of the second one?
Yes, so in this, the first one here, so these two are the same, right? This is how we write.
Mm.
We could write this way as well, but this is just a shorthand notation of saying rep is nested inside location. When the model runs, this is what basically happens behind the scenes. And this is what you would want if your random effects in this case they follow a hierarchy. They're not independent of each other, right? In this case, the block is dependent on where it happened, on which location it happened. So it's not just by itself on the area structure of this model.
Mhm.
Yeah.
Mhm.
But maybe there's
What if it is, sorry, what if we are not including location and it's just like a year stuff, like repeated like twice or 3 times yearly?
sorry, I don't think
Do we also nest the rep in the year? Like
okay,
if we are repeating the studies?
yes. So if the same thing with year, yeah. So if you had year, you would be like that. So rep nested inside year.
Okay.
Yeah.
Thank you.
Thanks. I think Omar had a question. Is that answered already?
Yes, my question was also about year, like time, but you already answered that. Thanks.
Great. Perfect. All right. So, I just added a whole, yes, Ariful, go ahead. Ariful, I cannot hear.
Yes, can you hear me? So if the year and the location are both, I mean, the 3 things, year, location, and rape, how we will organize, I mean, the nesting?
It's a great question. So there are different ways that you could do that, I guess, depending on and how you believe this structure works. For example, you could do, so if you have site in year, so, right, or location in year, you could do this. So year colon location interacting, and then rep nested in them. You could do this, which means that location is inside. So rep is nested in location, which is nested in year. If you have a reason for that, to believe that nesting, that structure is what represents your data, you could do the other way around. You could do rep nested in year, which is nested in location. Is also an option that you would have here. And then finally, the last option would be for you to create a new column that combines location and year. So let's say you create a new column, location and year, and under that use a paste 0 and you create like Midville 2022, right? And then Tifton 2022. with the full name there, you could also nest like that in that type of variable. Although that would give you the least structure. On the air. Well, this is getting more complicated in a direction that we're not going to export in code, at least not today. So, we could do a full exercise trying all these things, because really the beauty of it is you can try and see what happens. We're going to do some of that by the end of this exercise, but not related to multi-site year studies. So I just want to bring us back to our track here. But just since we talked about how to incorporate these new random effects and how they would be related to each other, these are some of the ways that you would specify them. All right, so coming back to our code, we just have one random effect and it's not nested in anything else. It's just rep, so that's how we would specify it. And then finally, we just want to call our data argument and say it was the RCBD DFW. That's the one that we wrangled above. So if you go ahead and run this, you should now have your object on your environment, your model object, RCBD mix mod. Let's ask for a summary of it and see how that looks like. All right, so now there's some more and new information here that was not here before. So let's just walk through this output a little bit and take a look at it. So first thing we see is a linear mixed model. It's saying that to us. Fit with REMO. If you remember, REMO is the algorithm that we want to use in mixed effect models, because that's the part of the algorithm that helps us to calculate or to estimate those random effects. REMO is not used in fixed effect models. REMO is something specifically that's used to estimate variance components in random effect or mixed effect models. So we see that it's telling us that you use REMO. There is another one that is, there are three other options really that we talked about in lecture, and REMO is the one that is recommended for us to use. It is using that by default, but you could change that on the formula here if you wanted. If you check the help of LMER, you're going to see some of the options you have there. It's giving us our formula, our data. So this is nothing new. It's just telling us that REMO criterion at convergence was a given number. So basically saying that REMO was able to converge to a solution of what your random effects are in this model. Sometimes REMO is not able to converge. If you have a very complex, complicated error structure, which we're going to see with the split plot, it may give you some warnings. It may tell you that the variance was close to zero and was not able to estimate it. So right now is a good thing that it says that it was able to converge. It's just information about that right here. We still have a statistical summary of our residuals. So these are the residuals of the EIJs, so the residual of the model that every model has. And now it has something new here. So it has this random effects side of the model. So it's basically telling us that there are two lines here that I want you to notice. There's the rep line under random effects, and there's a residual line under random effects. Both of them have a variance, both of them have a standard deviation associated with them. Something that's interesting here to notice is that the variance that was associated with the blocks, or rep in our case, was here about like 60,000, whatever unit this is. And then the residual, so the one that was associated with error of the model, was 376,000. So we have a lot more error that's ending up in the residual than it is being explained by the random effect of model. This does not have to be the case. It could be that your blocks, that you did a design, that your blocks were very well used, that you had that variability in the field and use blocks to contain the variability, and therefore the variance or variability that is associated with the blocks may be higher than the one with the residual. It could be. Yeah.
So in this case, does it mean that the blocks were not properly chosen in the field, or is it Does it just mean the blocks are not that different?
Yeah. Okay, so Jonathan's question is, what does that mean in relation to the block effect? So if you remember before, when we did blocks as fixed, right? I think blocks were non-significant, if I remember well. I don't know if anyone can correct me, feel free. But I remember that blocks were non-significant when we treated as fixed, which that gives us some indication that perhaps, perhaps we could have used a completely randomized design instead, right? And here is just giving us a proportion of how much variance is being explained by block compared to the error of the model. So I guess it's up to us as the researchers to decide if that is enough evidence for you to run CRDs in the future. What I normally do is, even if I don't have very strong reason, so even if I think that my material is homogeneous, I think it's still useful, at least for what I do. Maybe it doesn't apply to what you do, but maybe you can just follow me on my thought here and make a decision for yourself. I think that having a block is basically helping you to say, okay, I sampled this entire block here. Therefore, I sample one time each treatment, and that's like a timestamp for you. For example, sometimes it has happened that we're on the field sampling, and we start sampling on block one most of the time, and then it's going to start raining, in like 30 minutes. If you have a CRD, you're going to probably stop somewhere and maybe come back tomorrow, and maybe what you sampled today is not, most likely is not going to be balanced with what you sampled tomorrow, and maybe there is a rainfall effect on what you're measuring, right? If you have a CRD, you're out of luck. Maybe you're going to have to redo all measurements tomorrow, because then it's going to be unbiased. If you have an RCBD instead, maybe you can say, all right, let's try to finish block one today, and then we'll do 2, 3, and 4 tomorrow. And if there is an effect of rain, maybe that effect is going to be contained within the block, and it's not going to affect what you're measuring, especially if you're measuring things that really take a lot of time or are really expensive to measure. I think having a block just gives you that chance of saying, if I have to quit, I have like a checkpoint, Yes, Charles.
Still not talking. So I know that I've used SAS to run this model before, and then they gave us not SAS, job. They give us much more details about the variance effect, the random effects. So they give us like variance ratio, they give us like a log test to kind of see if it's significant or not. Like the variance ratio will just give you a percentage of like how much. I think it's probably like the division of the two variance. But we have more details to kind of decide whether log or your random factors.
So you're asking if that is available here, or just making the comments?
Yeah,
Okay.
but I don't think it's about. I think it might be available.
Yeah. So, okay, let me read that to those online. So Charles is asking here, he's saying that when he runs mixed effect models on JUMP or SAS, that the output gives a lot more information about the random effects, perhaps like what's the ratio between the variance between rep and residual, and maybe some other data, some tests about the significance. By default on the summary function, this is what it gives us. I normally don't really run like tests on random effects, like in this case, for example, because I'm really, at least in this case, by running blocks as random, our goal is more to just, so we have the blocks in the model, regardless of random or fixed. So that's already sucking into that noise that block has. And then here's just allowing us to either incorporate the block effect as a mean if you run as fixed, or as a random effect, or through the variance if as random. But I normally, in these cases, I'm not like, I guess what I'm trying to say is I don't really myself go in much depth on the random effects, other than checking the assumptions, which is what we're going to do next. Yeah, but I'm sure there are functions that would do those things. Maybe just have to do a Google and find what they are. Yeah. Okay. So again, looking to our output, we have this random effects table summary here, and then we also have our fixed effects table summary. Again, these estimates, they are based on that matrix restriction that we apply. So for ANOVA purposes, I normally do not really look into here. I go on my ANOVA table, on the ANOVA function to look into my fixed effects. And then just gives us here correlation of fixed effects as well, which is not something we were getting before. And that's pretty much what the summary function gives us for a mixed effect model. So I guess on my text here, Charles, I just did my own calculations. That seems like about 14% of the total noise is being associated with the block effect. Yeah, but yeah. All right, so let's check our ANOVA table, right? So remember that your model is independent of your ANOVA table. They're two separate things, two separate steps. So now if we check this ANOVA table, oops, RCBD, oh, I think I actually have a typo there. So it's RCBD mix mod and not mod mix. I think you're gonna have to fix on your side as well. But if we run this, so a few things I want us to notice here. So now it's calling this an analysis of deviance table, which is basically just because it is a mixed effect model. It's using a different algorithm to estimate those model parameters, in this case, Dremel. This is just the way that it refers to that approach. So something curious to notice here, I guess, is right here, you're not seeing the wrap effect on the fixed effect on the ANOVA table, I guess. Let me say that differently. So you're not seeing the wrap effect on the ANOVA table. The reason for that is that ANOVA tables will only show you the fixed effect components of that model. If we wanted to know more about the random effects, I mean, we could use some other functions as well. We got to see a little bit of that on the summary function here with the random effect summary. But what I'm trying to say is if you run RCBD with blocks as fixed, you would have rep or block as a line in your ANOVA table. If you run it as random, it is not going to appear there because it's not a fixed effect anymore. It's going to appear on your random effect side of the model, which is not incorporated into the ANOVA table summary. So just wanted you to notice that. All right, so if we interpret this, I believe it is the same interpretation as we've had when we ran as fixed, right? Which is we had our interaction significant, but our main effects were not significant, which means that then we
Sorry, Professor.
Yes.
Could you please repeat that why we are not able to see reps here in this ANOVA?
Yeah, so we're not seeing rep in this ANOVA table because the ANOVA table only shows us the fixed effect components of your model. So before, when we had rep as a fixed effect, rep appeared in our ANOVA table. Now rep is being treated as a random effect, and so it's going to appear on the random effects part of the model and will not appear on the fixed effects part of the model. So that's
All right, thanks.
just that, I guess, the distinction between treating as random and fixed and what type of model parameters your ANOVA is giving you information about. So ANOVA table only gives you information on the fixed effects.
Got it. Thank you.
Awesome. All right. So here, as before, we see that our interaction is significant and our main effects are not. I don't think this interpretation did not change from the previous analysis. This was the same interpretation we got. So based on this ANOVA table is how you determine how you break down your means. We talked about this already, that there is nothing that keeps you from your model statements. So in this case, LMER to your EM means. There's nothing stopping you there. You could go straight out if you want to get all the means, do all the comparisons. But by checking the ANOVA table in between those steps, so having the ANOVA table as one checkpoint here is basically giving you one level of certainty of what means, and therefore pairwise comparisons really matter. right? In this case here is going to be those for the interaction between nitrogen and potassium, just like before. All right, so before we, so we ran a model, we checked the ANOVA table, we found some significance, we want to extract means. Before, so mean in pairwise comparison would be already things that you extract from your model. However, remember that we always check our model assumptions first to make sure that the model we have is a good model. If your assumptions do not hold, then whatever you extract from the model is probably not valid. So we want to make sure our model is valid by checking its assumptions. Because this, so when we had our fixed effect RCBD model, we used the package broom to get this function augment from the package to just create our residual information, just to extract the residual information from the model. Now, because this is a mixed effect model, we're going to have to use a package called broom.mixed. I believe, I'm not sure if you already have this package, but if you don't, if you try to load this and it says you don't have it, then you know what to do. You just have to install it. If you already have it, then you can just go ahead and run the code after it. That is basically just going to extract the residual data for us and put that right within our original data frame so we can associate specific observations with specific residual metrics. And then we calculate the studentized residuals ourselves as well. So that's what that code did. All right, so, let's recap something here that we did talk in more depth about these in the CRD exercise, but we talked about some in the RCBD as well. But if you watch the CRD, then you already have heard this conversation in a little bit more depth, which is the assumptions of the linear model that we're going to check based on residuals. Now, raw data is going to be independent. So for that, we just look for no patterns in the residuals. We look for variance homogeneity or homoscedasticity. This is also somewhat related to seeing patterns, but also knowing your data when you collect it. So, so I work with nitrous oxide in the past, working right now as well. And that is the type of data that is normally heteroscedastic. So we have to do some type of adjustment on the model before being able to use the model. And homoscedasticity, one of the examples that we talked about was when you have that fan-shaped residuals, which we don't have in our case. And then residual normality and outlier detection as well. Something that I do want you to notice, and perhaps I'll tell you this and I'll give you a 5-minute break here and then we'll come back, is the fact that with random effects, now we incorporate the random effects or the variance components associated with that random effect specifically, which in our case is the block. And every time you have either a random effect associated, or if you have a variance component associated, whether with the random effect or with the residual of the model, they have assumptions, right? So if you remember, it was alpha I for block and then EIJ for the error. They're distributed IIDN with mean 0 and a given variance component. Those are the assumptions, meaning that now for random effects, we also have to check the assumptions of the random effect in the residual of the model as we were doing before. Okay, I think maybe this is a good stopping point to give you 5 minutes. And then when we'll come back, we'll check those assumptions of the random effect, of the residual, and then try to finalize our exercise here. I'm going to give you 5 minutes.
Bastos?
And was it out?
So if you comment off.
That's the.
So you would then for.
Yes, you go, you know.
So your problem was.
Go the path.
They try to install it. So I guess what
I
was
think
the
that's the-
problem? It was with W4?
Yep. Yeah, so that's the like, that's the, and if we go over to like here.
Well, let's do this.
There's
You can
that.
tell me where the first error occurred, and then I can help you understand how long it took you again.
Yeah. 30 meter.
Okay, so here's what's going on, which I don't know if this will, if, um. I don't think I explained this, but every time we have a chunk called setup,
The geo.
if you run anything else below, it's gonna try to first run your setup, because then there's index what you need to run the code, and then go to your actual chunk that you're running, like the model. So here, when you're running that chunk, is basically running your step first, and then you're getting stuck on those. And so this is where your data is. So if you just look specifically.
And then run it.
Warning campus fields. There's no package called matrix.
I mean, it's a process, it's stable, that's
Quite
quite
interesting because.
powerful. Here, keep this, what I'm super random.
So we go to the same, like then as you figured out already,
Before anything
it
else.
seems like when you package matrix,
So
right?
it was like.
And then when you try to install it, you're getting an issue as well.
Yes.
Yeah.
Installing is not the issue, but when I'm trying to run the library.
Either one.
So it's actually saying.
It's
it's
not
available. Hmm. What is your R version like? Let's see.
Classification for wetlands. Prominence, woodlands. Or maybe it's not, yeah, mostly wherever. Just not. Second.
Hmm. I mean, you don't have the.
Unless you want to.
So maybe for now, let's just try to put this comment off multiple. And where do you
Is
guys
it
around
on
here?
here?
The burgers are in some?
Yeah, I've been here.
People say they was to this, I'm not sure. Okay, so now this one, I mean, so multiple is what we do with the rest of the variants, right? So in your case, that's where you can. Okay, so linear is.
Sheet on that really quickly.
So we don't have expected shock.
They tell you. Maybe the cake answer. It's okay. I see a lot of like fun. Like, yeah.
I'm not sure, so what I would say is, like, I don't know the answer to it, but I would say is like, try to just put the error on Google. I'm sure other people have run into this issue as well. I would try that first, and if that is like, if you built with some forums and Stack Overflow, posts, and you cannot find solutions, then let us know, we may be able to help further. So that's interesting. Yes, somebody online had a question.
Yeah, so I wanted to use the opportunity to, so anytime we are forking and cloning, we already have the 2025 DSA. Do I need to delete the old folder every time?
So, I mean, that's what we did before we connected getting GitHub, right? But after we connected getting GitHub, that was the reason, one of the reasons for doing that is then you would not have to manually download the GitHub updates. You could just do a git pull.
Okay.
So if you were able to connect Git and GitHub, then you would not need to download manually anymore.
Yeah. So I mean, anytime we are doing a git pull, we need to fork and clone, right?
No,
Oh, okay.
no, you just do the pull. Yeah,
Okay.
I would say, Sweber, I don't know if we had a recording on it. I don't think we recorded a class. But if you wanted to like take a look into the instructions that I shared, maybe you could get a refresh on how to do that step. But it's basically, so once you do, so you do the fork and clone the first time, and then after that, if you were able to connect Git and GitHub through that entire ebook that we followed, then all you need to do is just a git pull. Yeah, but if you, yeah, I would say maybe reach out to Amrinder and he may be able to help you to troubleshoot what's going on. All right. Okay, so let's come back to our exercise. So we have some assumptions we need to check in relation to our random effects. And so that's what we're going to do next here. So if you come to the next chunk, left choose the object name, give it the assignment symbol. We're going to use a function called ranf, which comes from the LME4 package. This function extracts some information from our random effects. So Charles, probably if you like the LME4 is going to have a whole bunch of functions that will help you to get more information out of the random effects. I would explore there and see, like if you're looking for something specific, that's probably a good starting point. But so here we just give our model object name. So RCBD underscore mix underscore mod. If you just run that and you print it, it basically has this component of $wrap, which is just giving us the random or the variance associated with each one of our blocks in this case. What I want to do here is just sample this first component as a data frame. One of the ways that we can do that is if you just come here to the ranf function, right after it, we're going to use the bracket notation. So give it 2 brackets and then the number 1, which basically pulls out this first component of this object. So if you run that and you print it, then it just becomes a data frame with a column called intercept and then your values right there. So because we have so few levels, just 4 levels here, because we only have 4 blocks, it's really not really enough data points to be able to fully assess our assumptions. So instead of saying like we're fulfilling our assumptions, I guess we can at least say we're not overly not fulfilling our assumptions. Perhaps that's how we would go about it. So I left you the code here for the QQ plot, where we're bringing those random effects for block. Everything else we already done before for just checking the residual assumptions. This is how our QQ plot for the random effects look like. So again, we only have 4 points, so it's really difficult to make a really strong inference over this. But, you know, I guess it doesn't look terrible. So that's probably the extent that we can say here. If we have one of these blocks that were really off, maybe that would be more alarming. But you know, with only 4 data points, this looks okay. All right, so this was basically the one assumption we're checking here that we can check with our random effects is just that normal distribution of these random effects. Now we're going to check all of our assumptions associated with the residual of the model or the error of the model, which are the same ones as before. So if you run these plots, they are going to look very similar to before. They're not exactly the same as before. And that's because it's a slightly different model now, having blocks as random as compared to blocks as fixed. But the overall interpretation, at least here, does not change. Right, so I just left you some comments there of what we're looking for. So independence, variance, homoscedasticity, and outliers, and then some comments. We already talked about this in the previous exercise, so there's nothing too new here. Then we're checking the QQ plot for our residual. So notice that something that's really interesting. We do have a residual for each observation, right? So we're explaining each observation with our model, including rep, nitrogen, potassium interaction, and then whatever is left, whatever is not explained by that goes into the residual. That's why we have so many more points when we look at the QQ plot of the residual compared to when we look at the QQ plot of the block. We only have 4 blocks, so therefore we only have 4 residuals to check for. Or not residual, but 4 data points associated with it. All right, so QQ plot looks good. We're gonna check now our normality. Looks similar to before. Still, there's some slight changes, but overall, we still, we don't change. It doesn't change our interpretation of it. So after checking our model assumptions, we conclude that they are sufficiently fulfilled and met, and therefore we can use the model for further inference. So on every workflow here, our next step is going to be to extract the means first. Remember that this is the level where we establish that relationship between the factors. So here we're going to look into the interaction because that was the only factor in our ANOVA that was significant. And so the way that I'm proposing here is that we just compare everything against everything else. Remember, this is something that we can change, that for a two-way interaction, there are 3 different ways you can show it. So keep that in mind, as that could be important for your research. So we're just getting everything against everything else. And then getting our pairwise comparisons as well. So same code as before. I'm just what's changing is the model, right? And behind it, what also may be changing is the standard error. So something for you to remember is, if you have your data and you're running a model with it, as long as the data is not changing, your means are, I mean, I don't want to say never, because I'm sure there may be exceptions to this, but means are not really affected by how you treat your the randomness of what you treat as random or fixed in your model. However, what does change is the standard error, both of the means of pairwise comparisons, of the error that's taken into account when you do p-values in your ANOVA. That is changing, which basically means everything important about your model is changing, right? So if your error increases or decreases, depending on the model you're using, that trickles down to everything that's important about your model. So we're going to take a look into some of that in a second here. So we have our letters again. We do that the same wrangling as we did before to get the letters into a data frame format, remove the white space, and create a treatment name. So I'm just going fast over this because we've already done all of this before. And then creating our last plot, which is going to include raw data and a statistical model summary in the same plot. I think I left you all the code since we have already done a lot of this before. So these are the letters. Remember again that the way that you design your plots should be intuitive and match the way that you extracted your means, right? So we talked about, if depending how we get the means of this two-way interaction and do the pairwise comparisons, maybe this type of plot would not be the best. You maybe have to do a facet of some sort to make sure that you're being intuitive with your audience. All right, and then we can just export this as well. So I have a quick in-class assignment for you. So it's not a quiz, it's an in-class assignment. But I want you to just maybe us to take a quick step here, quick step back and think about. If you can remember, what were the things that change between running block as fixed and running block as random, at least that you can remember based on the script, not necessarily on the results, because you're not comparing results side by side yet. But just on the script, what do we change in this entire script that makes it a mixed effect RCBD compared to a fixed effect RCBD, which is what we did before?
We indicate the rep.
Okay, so we changed the model specification, right? So we used a different function and we indicated the wrap was random. Okay, so secure, that's all right. Let me see here. For those in the room in Tifton, can you guys tell me, maybe one of you tell me your name because I cannot quite see you, and then your thoughts. So what else changed between our fixed effect analysis, assuming blocks as fixed, and our mixed effect analysis, assuming blocks as random and nitrogen and potassium as fixed? And you can look into your code as well. I'm just showing here the last point that somebody brought up, but this is not the only difference.
While extracting the residuals, we didn't use the broom function or library when we used the broom.mix.
Right, so Comfort is saying the residuals are a little bit different, so we use a different package. I mean, the same name function, but from a different package. And then we also got some residuals, or not residual necessarily, but some information about the variance related to the random effects, right? So that's something that was not here before with when blocks were fixed. So notice that if blocks are fixed, you're really not checking the assumption directly on blocks. You're checking the assumption on the final residual, which, yes, it is impacted by block fixed in the model, but block doesn't have its own dedicated assumption at that point, which it does in a random effect model or a mixed effect model for this matter. Yeah, and I mean, as far as what we did, that's all. We just changed our model specification with a different function and specifying reps as random, and then check the assumption differently. Those are the two main differences on the coding side from a fixed effect blocks as fixed and a mixed effect blocks as random. Everything else is the same. Right. So I just wanted for you to appreciate that difference as well and understand that. Okay, so thanks for those who helped. Now I have an in-class assignment that I want you to work in pairs. If you can work in pair, if you are in a place where there is an even number of people, then partner with your neighbor. If you are online and you don't have somebody next to you, then I guess you're gonna have to do this by yourself, which is possible, is doable. And I'm gonna give you until the end of the class to submit the assignment. So it is an in-class assignment. It's not just a quiz, it's an assignment. What I want you to do is go to ELC. Let me go myself as well. And let me make this assignment visible. All right, so it is visible to you all. It's called assignment 5, comparing blocks fixed versus random. The reason why I'm asking you to partner is because what I want to ask you to do is if you are in a pair, then one of you, so first off, maybe clear your environment of all the variables you created today, right? So you would do that. Well, let me show you how to do that because I don't think I've showed in the past. So you can come here, click on that broom icon right there. This basically clears your environment, basically removes all the objects you created. So again, this is the broom icon you're looking for to clear your environment. So one of you runs the script RCBD partial, which is the script that we did RCBD with blocks as fixed. The other one runs the script that we did today with blocks as random. If you're working in pairs, each person does one. If you're working by yourself, you can run one script, clear your environment, run the other script. As long as you don't close the script, the outputs are going to still be below the chunks, and then you can compare yourself if you're doing it by yourself. So my question to you is, I want you to look to help each other in pairs and look into the outcomes of these two models. As far as it relates to the following, I want you to look into your ANOVA table p-values. So on the ANOVA function, you have p-values. Tell me if they changed, and numerically, if they are different, you don't have to give me the number, just say, the fixed effect had a lower, higher p-value for nitrogen or something. And tell me if the overall interpretation changed as well. So, maybe the p-value changed from 0.01 to 0.001. So it changed, but your interpretation did not. You still are considering that as significant. And then looking to your EM means. So from the EM means function, I want you to look at the means themselves and at the standard error and tell me if you see differences, if changed, and in what way. If something increased, like standard errors increase under this model compared to that model. That's what I wanted to tell me. And then on the letter separation, I wanted to tell me, did the letter separation change when you compare these two different models? So this is basically the assignment that I have for you. I want to remind you that for you to be done with today's class, you need to claim your attendance. I don't know if Arminder has opened the issue yet. Let me take a look. Okay, so Arminder has opened. So for you to be done with today's class, you have to claim your attendance. You have to submit the assignments. Even if you're doing in pairs, you are still gonna have to submit individually. Even if your answers are exactly the same, that's fine. But you're still gonna have to submit individually on ELC. And then finally, I want you to do a git stage, commit, and push after you're finished the assignment. Yes.
Basically, my computer, my charger. So I'm using. Push.
Oh, yeah, that's okay. You can do later. Yeah. Yeah. All right. So again, for you to be done with today, you have to submit your assignment, claim attendance, and do a git stage, commit, and push on your 04 RCBD exercise. All right, I'm gonna let you work together. If anyone has any questions, I'm gonna be here. Just let me know.
Dr. Bastos?
Just one sec, Comfort. Yeah.
It's an odd number, so
Sure, yeah, that works. Yeah. Yes, Comfort.
How are we submitting the assignment? Is it on the same script file?
No, so I just want you don't have to submit any scripts. I just want you to write down on the assignment answer. Just tell me what you see, like lower, higher, this is higher.
Okay,
Yeah, just with plain text.
okay.
Dr. Bastos.
Hmm?
So for the random effect model, how do we check the p-value for the block effect for the rep?
Oh, you don't have to check the p-value for the block effect. Yeah.
Okay, so you just want us to compare the p-values for the main effects and the interaction effect
Yeah.
and their subsequent standard error and later separation.
Yes.
So can I note it down? Okay, so you need to write in here. All right, thank you.
Yep.
Robertus, the sum to zero argument applies to other experimental designs too, like split plot and
Yeah,
or with
so
the-
that sum to zero, especially when you're looking at an ANOVA table, is where you want to have that applied.
All right, thank you.
I mean, for the interaction with them last week. So this doesn't get, it's just.
Dr. Bessis?
Yes.
Will we write it on the Microsoft Office and then send you the file? I didn't get that part. Where we will write it? The answers?
You can just write directly on EOC. There's
Oh,
like
okay.
a text window or prompt that you can just answer there.
Okay. Thank you.
Slower.